written here, good designs protect the investment. The truth is, no matter how good a design you make, no matter what materials you use, the structure is not going to last forever. It's going to deteriorate at least. Some of you have perhaps an old car. You know things require maintenance. You know also that we can have good designs that will be designs that require far less maintenance. And when they require far less maintenance, then it means they are more durable. They last longer, and that's important because a bridge is actually a quite expensive structure. Yes, I know you can get bridges for a few millions, but then again, you can also spend 10 or 50 billion Danish kroner on them. And, well, we have seen designs which did not last. Otherwise, what I'm going to do in this lecture, I'm going to try to explain why things like inspection, maintenance, and repairs must be considered during the design. I have to stress that you have to plan the maintenance to ensure the service life. Again, this is not different from a car. If you buy a new car, you know perfectly well you have to go to the mechanic, say once a year, and let him go through the car, replace the oil, etc. And the last thing is, well, it would be nice if designers like you, if you could identify the critical points in the structure and perhaps plan for the maintenance. This may not be a part of this project you're working on, but it's so much easier to inspect and maintain a structure if these activities have been considered during the design. To get through all these things, then we have to look at these things here. Think, okay, average bridges. Average bridges may not have anything to do with what you are designing. You're perhaps designing some extraordinary bridges, but still, it's good to know what have been built because that also gives us a very large flow of experience. We have to talk about what it is, what the management cover. We have to talk about why we need background data to the inspection and what types of inspection we have. And then we can do an optimal management, and yeah, well, I don't know if you have realized it, but our knowledge is not perfect. It's not complete. And if you go out to an existing structure, then it's even more incomplete. That can be a bit of a problem, and then a few tools, and well, we talk about, I would take a so-called concrete case. We had a wonderful bridge, and I tell you, there was everything wrong with it. So, in a way, it was really an engineer's dream, because whatever you want to look at in deterioration would be present there. Whatever potential solution you could come up with could be useful here. When we talk a little about what you must do as designers, and we look a bit at the trend. And why are we talking about the trend? Well, that's mainly because you can go about bridge design in two ways. You can either do things as they have always been done. That's easy to plan, and you also even know when the problems are going to show up. And you know how you handle these problems because you may have colleagues who have been doing that for 40 years. The trends are more an attempt to try to avoid these problems. Some are expensive, some are cheap. Well, anyway, our average bridges, well, same all over. Most of the road bridges were built in the 16th and 17th. Why is that important? Well, it's important because it seems that when a bridge becomes 25 to 30 years old, then that's where you see the serious problems showing up. I mean, the deterioration starts at day one, but after a number of years, then say the salt will have reached the reinforcement, start corrosion, the paint on the superstructure, steel structure will start to be defect, and that will lead to corrosion. So that's about the time where you 25 to 30 years, that's typically where you start to see the problems. Then of course, that was the road bridge, the railway bridge, the far over. And the far over because I don't know how many of you are from Denmark, but are there anybody here who can remember when a new railway was built the last time? It's probably about 100 years since we built a railway. Except things like railway line over Amager to Øresund bridge. But the rest of the cases, the railways have been in place for, say, 100 years. We have not replaced the bridges. Railway bridges can be 50, 100, 150 years old, and some of them are in deep trouble. Well, of course, we have a wonderful case here in Denmark. They had to close a railway bridge immediately because they found a 25 centimeter long crack in the steel structure. And that have sort of stopped quite a lot of the railway traffic to the islands south of this island for a period. And, well, anyway, that was really a case of too few inspections, because I know there were cracks in that structure 10 years ago, so they just didn't follow it properly. Well, let's go to the typical road bridge. Well, you will see a lot of these very simple bridge, essentially just a concrete slab supported at the end and a couple of plates in between. Very simple. We have older bridges like this, more curved. This is not a normal structure nowadays. It's too expensive. The reinforced concrete bridge can also be bridge with triangle spans. Actually, what you have here, that's the concrete. What you have here, that's the superstructure, which is in steel. It's very common to mix concrete and steel in bridge structures. Okay, now all things we have to consider when we manage bridges. That's really the traffic, because I mean we have seen quite a growth in traffic. If you look at the traffic growth in goods or in persons, then you can see a lot of transport types like buses, railways, buses and railways, which are constant, where we have the large expansion. That's in the cars. The amount of traffic grows typically with 2 to 3% per year. That means that in 25 years or so, you're going to have twice as many cars on the road. In 50 years, you're going to have 4 times as many cars. That's probably not going to continue, but manage bridges as traffic planning. Also, if you want to plan the maintenance of a bridge, then you would look at this traffic forecast. Because if you can see that the bridge is too small, too narrow in 10 years' time, then you're not going to spend a lot of maintenance on it, because you know it's going to be replaced. I said that trains, there were not that much growth in the traffic there. And that is except when they change the traffic pattern. Now, it seems we are going to get a new tunnel under the Fehmarn Belt. If we get that, then all the railways down to Fehmarn will have to be enlarged. If we get it, then we will need 2 tracks. If we don't get it, we will need only 1 track. And that was really why they postponed the replacement of Masmid Sons, or the bridge they had to close. There's only 1 track. They didn't want to replace it until they knew if the new bridge should carry 1 or 2 tracks, which was a very good management decision. The only problem was that they cut down on their inspections, it seemed. Yeah, a little bit about cost and capacities. Well, this is actually one of the most interesting slides, because it contains 2 important informations. We spent about 1% of the gross domestic product on building new structures for the infrastructure. We spent 1.5% maintaining those we have already built. And as we can see, that obviously all these structures get older, then it means that they will require more and more care, and we will see that 1%, 1.5% increasing, and we will probably see the 1% for new structures decrease. So it's actually quite important to be able to plan the management. And yes, let me repeat this at the start by saying that nothing lasts forever, at least not without maintenance. And if you're thinking, what about the other construction areas? Then I would say it's equally true for the other areas. Now, if any of you have questions, you just raise a hand and I'll try to observe you and let you have your question. Otherwise, you can take questions when we reach the break. Well, but I will continue until I think we have a suitable time for having a break. Bridge management, what is it? Well, it's really everything about running the structure. That means it's simple things like traffic regulations and trying to minimize the number of days when the bridge have to be closed due to wind, snow, ice, etc., and maintenance work. It's also about making sure that the structure is safe. Because that's, if the structure is deteriorated, then we can always discuss when we should do something about the deterioration. But if the safety is not sufficient, then we need to close the bridge right now. And then we have to fix the problem. And things we do there is we do the inspections, we do some preventive maintenance, repairs, rehabilitation. Let me explain what these things are. Again, you don't know that much about bridges, but you probably know a bit about old cars. Especially has started to corrode, we would then give it a new cover. Rehabilitation. Well, there's a fine distinction between repairs and rehabilitation. Rehabilitation is, you might say, a really large repair, perhaps even an upgrade. With a car, rehabilitation could be putting two new doors and a new engine. I mean, major thing. A bit about ordinary repairs. Okay. Before you go out to do the inspection of a bridge, say a 30-year-old bridge, then you need some background data. It would be nice and useful to have the original drawings and calculations, because suppose there's a corrosion problem somewhere, then you would like to know if that was an area where you really need all the reinforcement, or it was an area where there are 3 times as much reinforcement as you really need. One of the things you'll learn very quickly is there's a term as built. You see, the drawings you probably get access to are the drawings made by the designer. When they built the bridge, then the contractor gave it from the original design. He would discuss it with the supervisor, but he would normally be allowed to make changes. It's not always the owner of the bridge paid for getting his drawings upgraded. So that's one of the very interesting things you always look for. Do I have as good drawings, or are they just the originals? Then another thing you want to find is the old inspection report. I mean, if the bridge is 30 years old, you're probably not the first engineer to go out and inspect it. And for your planning, it is very, very convenient to know what are the system have to make estimations of costs, and have to estimate how fast these costs will grow if it's postponed, and then it starts to be complicated. This is why it's not complicated for one bridge. That's just, I would say, a bit of work. But if you have to put it into their overall plan where they have thousands of bridges, then it's a bit more complicated. Okay. Now, inspections. I would say there are a couple of things we need to say here. So, the first one is access. We really need access. Yeah, well, can you see these pictures? Good. Well, we need access to the structure in order to do the inspection. Two simple examples here from the bridge. Here we are inspecting the lower side of the bridge deck. The upper bridge deck, you see no trouble about the access. We have a train who runs in here with a lift on, and it's easy to access. It's easy for us. It's not easy for the people with the railway, because once you place a train here, then they can only use one track. This means you cut the railway traffic with 50% at least in that time, if not more. Inspecting the pylons? No. In a way, that's a whole lot easier. I can see, I don't know if you can see, we have two inspectors here. They are going to go down the side to do an inspection. How are they going to do that? Well, they are mountaineers. They have each a cable which they fix to the top. This is not something where they allow anybody else to enter. They tie the cable to the top. One cable for each office, and then they go down the side. That's not what I would call easy access, but at least there were no traffic regulations. The other point, I'm going to talk about three different types of inspection: routine, principal, and special inspection. And then the fourth, which is not really inspection, but which is a step forward, monitoring. Okay? Now, inspection. Yeah, well, the first thing I would say is it's sort of impossible to do an inspection if you don't have access to the structure. I mean, you do want to get very close to the structure to have a good look at it. Sure, we can make some very fast inspection where we just stop at the side of the road, go out, bring our binoculars out and look at the structure and say, well, yeah, it looks fine. But if you really want to have a good look at it, then you need to get closer to it, and for that you need access. And that access can be difficult, like on the pylons. It can be inconvenient as, well, you have to block the railway. It may very well require traffic regulations, and I mean, we have all driven on the highway, haven't we? We have all met a traffic regulation. We have all been stuck in the queue. And that can actually cost quite a lot of money. Now, we are engineers. So, if I can find a piece of chalk, let us make a small estimate. We take one of the highway bridges with quite a lot of traffic, stuck in such a queue, I mean, just a rough guess, how much time would we waste there? 5 minutes? 10 minutes? Let us say 10 minutes. Each person wastes 10 minutes there. Now, what price did we put on the time wasted in queues? Well, we say 15 euros per hour when it's about minimum salary here in Denmark. Ah, 60,000 passengers who waste 10 minutes is the same as 6,000 hours wasted. Multiplied by 15 times 90,000 euros per day. Now I'll call that a fairly substantial sum. I mean, and in a way, you might say, but who are losing all this money? Well, essentially nobody, but if people had spent these 10 minutes working instead, then we would have gained quite a lot. So, you can see these passenger delay costs can be quite large. And that delay I talked about, that was for the cars. In a way, it's very easy to make a traffic regulation on a highway. It takes about half an hour to set up, about half an hour to remove, and people are extremely flexible. Also because if it's really a major problem with the highway, then there are normally other routes you can use. If it's the railways, then it seemed as a small and innocent problem, but it is not. Take that problem with the Øresund link. If we block one track on that railway, then that affects, all passenger traffic between Denmark and Sweden. That means it affects the railway traffic in Sweden too. It even means it affects the passenger traffic in northern Germany. I mean, such a delay will spread out in the system. They can accept it if it's planned. So they have a couple of months to organize things. But it's, I would say, it's problematic. And it affects a lot. Now, I worked with bridge management until 2005. So the prices I'm going to tell you may have increased. In 2005, if a contractor made a mistake where he delayed a train, he had to pay a small fine, 500 kroner. You might say, that's nothing. And it is nothing. But as they say, well, yeah. But what if it's the first train in the morning you delay? Then the rest of the train traffic will be delayed for that day. So you may end up paying for 450 trains times 500 kroner. Then it's about a quarter of a million. So, I mean, in contrast to the cars, then the traffic with the trains are much more vulnerable. And, but still, I think it's fair to say, yeah, inspections can definitely disturb the traffic. Yeah. Train situation here with a lot of queues, and we have one here with very little queues. The explanation, well, there were not that much queues on this photograph, well, that's because it's almost 30 years old. There were not when we look at cars. We look at trains, well, for these delay reasons I told you about, we will often be forced to work at night. We could be forced to do the inspection on the inspections without traffic regulations. And doing the inspection without traffic regulations, you might say, what about the trains? Yeah, they run very fast. This is why if you do inspections on a track, say if you want to inspect this place here, then you would have your personal guard standing by. You would be assigned a guard whose job it was not at all to talk with you. His job is to look to the two sides and see if there's a train coming and be in contact with the traffic administration to get a fair warning. Now why that? A small calculation. A train runs 180 kilometers per hour. Now, how long do you think it can move in 1 second? 5 meters? 10 meters? 20 meters? 50 meters? 100 meters? 60. Actually, the right answer is 50. It moves 50 meters per second. Now, suppose you are an engineer, you are out there doing an inspection. How many seconds do you say you could be distracted by an interesting detail? If we say 20 seconds, it means that the train can move 1 kilometer at least during these 20 seconds. This is why you have a guard standing by, and they say, this is the maximum distance it can be away from you. Because his job is not to say, dear sir, I think it would be a mighty good idea if you step off the track. Well, he can do that if the train is far away, but that took me at least 10 seconds to say that. The train moved half a kilometer. No, his job is to say, you better get off the track now. And yeah, you have to physically pull you off the track. I would say it's a scary experience first time you get dragged off the track like that. But then you normally see the train coming past you with 180 kilometers per hour, and you're very grateful. In a few situations, you are able to work on a track which they don't use that day, but otherwise, you normally end up working at night. It could sound as if it was a good idea to work during the night. Truth is, people are less effective there. The other truth is, we use the railways for passenger trains and for transporting heavy goods. These two types of trains cannot run on the same track at the same time. Passenger trains run fast, stop often. Heavy goods trains drive slowly and hardly ever stops. So they run during the night. So it's going to be a problem. Always going to be a problem. And a good indication of that is when you have a budget for inspection or maintenance, then you will see 60% of that disappearing into traffic regulations when you work with the railways. Well, okay, then there are a few, of course, some cases where we don't need traffic regulations. These are some of the poster photos from inspections of the Great Belt Lanes pylons. I can say the way they organize it is that about here there will be two round steel eyes where you attach a steel wire top. You pull the steel wire over the top and down the other side, fix it here, and then you build a platform which hangs in the wires, and then you can move on there. No as he said, well, it can take you guys 20 minutes to get down from the platform, and it normally takes the clubs 15 minutes to reach the pipe. So, occasionally we had to get out fast. Anyway, I would say it was a beautiful view from up there, but quite time consuming. If the designers have thought a bit more about how to do things, then we wouldn't have been in these situations. But of course, that was great. But at least we had a platform. Here you see one of the Swedish mountaineers. These are the roads he hangs from. This is, I mean, and if they break or fail, then he would fall all the way down. I would say that was actually quick and fast, but not really convenient. And I don't know what they're going to do if they ever need repair work. Yeah. I will take one slide more. I've seen here, well, a part of a principal inspection. We have different types of inspection. We have the routine inspection. That happened very often. And the person that we use for that, well, we can say, you don't need a lot of education to do this. Can be done by the maintenance crew. Normally, people will anyway have maintenance crews there. You may have seen some of these crews, because those who do the maintenance, the routine inspection on the bridges, will also be those who empty the disposal baskets near the bus stop at railway line. I mean, they drive around and they pick up garbage, they look at the trucks and say, well, is there something wrong here which might require that we send it out a more qualified person? Well, this would be the totally routine inspection. Then we will say once a year, twice a year, send out somebody who knows a bit more, and he will focus on just checking the bridge. And this report would really be standard report. And just to illustrate how fast it goes, I had a colleague, Peter. He had this very important job every year to inspect 400 bridges. Only thing was, they wanted the report before Easter. And Peter said, well, he preferred those winters where there were not that much snow, because he could only start his work when the snow melted. So sometimes he had like 2 months to inspect 400 bridges. He did it. I think he had a bit of overtime there, but you can imagine that must have been fast. If we assume, say, 40 working days, 400 bridges, then yeah, he would need to inspect about 10 bridges per day. That has to be fast. And he can of course write in the report, well, this looked perfectly normal. Or he can say, well, I want a principal inspection, because there's something here which I think could be quite serious. And now, principal inspections. I mean, we have the routine inspections. With the routine inspections, they just go out, have a look at it, don't spend that much time on it, and then they say, well, there seems to be something wrong here. Could be corrosion. We noticed that there's this is something we more or less only do when it's required. Some countries say, specified by law, it has to be so and so often, but we say, well, it should be between every year and say every 6th year, depending on the condition of the structure. And the purpose of these things is really to detect the deterioration before it gets really serious. I mean, if anybody asks me, is there corrosion in this bridge that have been standing for 10 years? My answer would be, yes, of course there's corrosion. And by the way, what bridge are you talking about? Of course there would be corrosion. It would be in a marine environment with salt water, or it would be somewhere where we use de-icing salt. Of course there would be corrosion. But it's not a problem. Unless it seems to get serious. And this is why we do the principal inspections. And in the principal inspections, there we need more physical access. We need to be able to get really close to the structure, because it can be very difficult to see the damages if you are 5, 10 or 50 meters away. And of course we raised what are the needs. We try to describe the damage we have seen. We take pictures, lots of pictures. We try to identify when we should have a closer look at it next time. We do also decide if there's a need for even closer or special inspections, or if we straight away can see that this is bad and you really need to repair it or rehabilitate it. If you have a large bridge and you see the concrete cover have fallen off in a number of positions, and you know there's a lot of water and salt in the environment, then you will immediately say, oh, there's a need to do something here, and you would make an estimate of what it would probably cost to do this or that. And I would say these reports tend to be large, because you want photographs of just about everything you have inspected. I would say the worst I have met was Öresund Bridge. There they wanted measurements of every single crack in the concrete structure. Until they heard the cost of that, then they just wanted those with a certain crack width. The larger the crack width, the larger the crack, the faster will salt and water penetrate, and the faster will corrosion go. They wanted photographs of all of them, measurements of all of them, and registration with the GPS. I think those who asked for it were people who had never been in the field. But anyway, the registered recommended you give a condition rating of the structure. We have a scale from 1 to 5. 1 is perfect, 5 is, well, it should be close right now. You will also give a rating of how fast you think the deterioration is going to go. It's not so much for the purpose of estimating the deterioration, but it's for estimating how fast the price of repairing would increase. Okay, you try to identify which elements should be repaired. I mean, if you have a bridge with 10 columns and so equipment do we use for these principal inspections? I would say very little. Pen and paper, camera, a hammer to bang on things to listen to how they sound. We would normally have one the rest of the equipment. Usually have something so you can measure positions, and we would have such a card like this with small stripes on. That's really to measure the crack width in the concrete. You place it up against the crack and you say, well, yeah, 0.15 millimeter width. Simple, robust, old-fashioned. Well, that's what you use here. No equipment. And why that? Because, well, equipment is expensive. Equipment takes time. And if you have to inspect 2 kilometers of a bridge, you do it visually at first. And then you may call in somebody to do a special inspection. But that will not be the whole bridge. It will be like, there are these 2 columns. I want to know what is going on in the lower 2 meters of them. It looks back. And there's a spot in the superstructure where there seems to be a lot of corrosion. Let's have a look at that at the same time. And then you say, well, it could be this or that or that. Fine. If it's this or that, then we need these and these equipments. These instruments. And why do we do it? Well, we could, of course, just go ahead and make the repair. It's a whole lot easier to plan the repair if you actually know what the problem is. And it's also often possible to postpone the repair if you know what is going on. Because it might look bad and turn out to be no problem. And the purpose of all these things is, of course, to spend the money in the best possible way, to extend the service life, and to minimize, say, road use and convenience costs are both loads are calculated here. And yes, it is to avoid unforeseen costs. Sometimes, when they start the repairs, and they remove the damaged concrete, they remove the pavement, sometimes you look at it and you realize that things were far worse than you imagined. This is where the costs explode. And yeah, purpose of it, yes, that is to get additional knowledge. It's also to set up the different repair strategies or rehabilitation strategies. Again, let us take the case of your old car. Now, we all know old cars start to have problems. You inspect them from time to time to make sure that it doesn't simply break down. You inspect it from time to time to do the proper preventive maintenance, like giving it a treatment to reduce the corrosion. You will in the end end up in a situation where you can see that now I need to do a somewhat more expensive repair. And that will probably last for another 2 years, and then I have to same thing with a bridge like any other structure. You reach a point where you say, well, I can do this. Doesn't cost that much. It will last 5 years. Then I have to repeat it. I can do another repair that will last 15 years. It will cost more. I can give it a major renovation. Will probably last 30 years. Or I can buy myself a new bridge. Taking a new bridge is the most expensive thing right now. But the repair costs in the next 10 years will be pretty small. Of course, you don't have an infinite amount of money to buy new cars. The road directorate don't have an infinite budget for buying new bridges. So, you and the road directorate have to look at these different strategies and figure out which of them would be suitable. Yeah. Okay. What methods do we use in the special inspections? I would say any method that works and isn't too complicated. At least it's some that we use in for the concrete structures. We focus a lot on water ingress, chloride ingress. Chloride is a part of the salt that causes corrosion. We focus a lot on the corrosion. The corrosion is an electrochemical process, which is why we typically measure the potential of the reinforcement, because that gives us an indication of the risk of corrosion. It also gives us an indication of where in this structure it might go wrong first. We try to measure the corrosion rate. That would really be the interesting one, because we don't want all this corrosion. As long as it just takes a couple of 100 years before it's a problem. If it only takes 2 years, then we want to have it stopped immediately. Then we have things like the smart saver, angle, and georadar, where we can look for defects. Especially in concrete, we often have cracks. Well, we can have cracks that penetrate from the surface into the structure. These are easy to detect. You use your eyes. Then the other type, they run parallel to the surface. Obviously, you can't see them on the surface. But you can use things like these to make a so-called non-destructive testing. And you can map the whole surface and you can see where things happen. Then of course we can also drill a small hole and use a bow scope. Doctors use endoscopes, so they can inspect us without cutting us up, and they would normally start by sticking the endoscope down in the throat. If they don't find anything there, they will try from the other end. We use somewhat the same thing. We just don't want a flexible one. We drill a hole, and then we can insert our bow scope, and we can see what we see in there. It's easy to see the laminations. And we only have to drill a hole about 10 millimeters. That's easy to drill, it's easy to plug afterwards. And some of the things we look for, well, of course, we always look for moisture content. If there's a part of the structure that has a higher moisture content than the rest, then we probably have a problem there. We look at the chloride content. Chloride was the part of the soil that gives us corrosion, and if we look at a profile of that, then we can get a rough guess about how fast it penetrates. Yep. We could take samples from the concrete. If we think sometimes it's difficult to get the drawings of the structure, as it is really big and as it has been repaired. Then what about the concrete quality? Well, you know what we asked for, and if we got what we asked for, we wouldn't have a deterioration problem. So if we have a deterioration, then we should probably check the quality of the concrete, and we do that by taking samples seen, well, a calcium reactivity. That can be with orange flint or the white color, like normal color flint stone. We had an ice age, crossed to the flintstones, it makes the remains of that with the good gravel. Problem with these things is they react with the salt, and then they absorb water and they expand. And if you have a lot of aggregates, a lot of sand grains in the concrete that expand, then you have a lot of cracks and you may see the concrete falling apart. They replaced the crash barriers on Lyngbyvej most of the way. But up to about 5 years ago, you could see them simply falling apart. That was because they used aggregates that were reactive. And when they are exposed to water and salt, then they fall apart. Yeah. Special inspections, yes, well, we have to look at different strategies. Should we take the smaller repairs, should we take the largest, and we have to estimate all the cost over a 50-year period. Why do we need that? Well, I said we could take the cheap repair that would last 5 years, we would take the more expensive repair that would last 30 years. How are you going to compare that? Well, you can only compare that by looking at, I don't know, a 50-year period and say, what would it cost in average? And then, of course, we look for inflation, etc., and we calculate the so-called net present value. And the optimal strategy, well, that's the one with the, well, that's the cheapest one. And, of course, when we look at the different strategies, then we have to say, okay, discount rate could easily vary over the years. I mean, these years, the interest rate is exceptionally low. In 5 years' time, it may be somewhat different, okay? We try also sometimes to introduce new technology. What is that? That could, for instance, be to say, okay, we could install some kind of monitoring. Could be very advanced, could be very simple, but something which would enable us to follow the structure easier. It can just be insert some sensors and have some cables so you can actually make a measurement without blocking the traffic. And you can make the measurement when you pass by that bridge anyway. What we often see is that increase, it makes the inspection a bit more expensive, but in the long run, it makes the maintenance lower. We spend less money on maintenance. Yep. Staff, which we use for special inspections, I would say that would be a report on a, well, more or less scientific level, because the people we use are really experts. And I use the word in plural because we normally have to involve more than one specialist. Has to be somebody who's very good at this deterioration stuff, who's very good at using and interpreting that instrument we use, or who is very good at microscopical analysis. It's very rare that we have somebody who is an expert in everything. Actually, I don't think I've ever met one. If you're into anything with deterioration, then these people are very interesting people to talk with, because they have quite a lot of knowledge, both about theory and about practice, and they know how to work in reality. Okay. Next step in the inspection. This is really the top. This is where we say, okay, we set up some monitoring. Instead of like specific point, or 10 specific points, which means you follow these points very detailed. But because of that, then you must always combine it with something else, like say, a mapping of the corrosion activity. If you have a map, say, okay, this large area corrosion were like this and this on this date. Then you insert sensors in pre-selected spots, and you follow it how it develops in time in these spots. But you need to combine it. Yeah. Optimal planning, yeah, and of activities. Well, challenges in these things. Well, how can I put it? We just don't have enough money to maintain the structure in perfect condition. We would love to do it, but it's totally impossible. And still, we must, with limited funds, make sure that the safety is sufficient. We must also ensure that the capacity is sufficient. I mean, an easy way of keeping a railway bridge in function would be to block the heavy traffic. Of course, that would work. But what would that do to the transport capacity? It would reduce it a lot. So that's normally not an option. Yeah. Jump forward to the limitations. Well, I said that we have not enough funding to maintain the structures. Well, normally we don't even have good budgets for doing the inspections. So it's more like a rough guess, really. But even if we had enough there, and we had a few problems. The first is our assessment of things are, well, quite uncertain. Prediction of how fast the damage is going to develop, well, they're also uncertain. And then there are some preventive actions and repairs we can do. Well, quite frankly, we are not always sure they work as well as we plan. And the cost of having anything built, well, surprise, surprise, these costs are also uncertain. And let me illustrate it. We do, for instance, often drill out a core from a concrete and we slice it up and we measure how much chloride, how much of the salt have penetrated into it. And then we know that if there's a concentration of 0.05%, then we probably have corrosion. Some says, no, it's better with 0.1%. And then when we take three cores, I mean, at least we're taking right beside each other on a concrete wall, which faced the highway, taking about this distance from the ground, this distance between the cores, took three. And you might say, oh, that looks somewhat the same. Yeah, reinforcement is in here. If I should make a prediction of when corrosion would start, then that prediction could range from corrosion starting when the bridge is 37 years old or when it's 53 years old. Normally, we don't take three cores, we take one. Add to this that we are actually uncertain about how much chloride we need for the corrosion. Could it be 0.1%? Well, in that case we can add almost 20 years to the structure's age. This looks bad, but it's worse. Because remember, when we go out and inspect the bridge, it may be 30 or 37, 35 years old. If it's 35 years old, then this year will say, you start corrosion in 2 years' time. This one here will say, well, you start corrosion in 42 years' time. It's a world of difference. 2 years' time is, well, we should probably do something about it. 42 years, it's like, forget, we'll look at it again in 20 years' time. Next problem. years before you repair. We do have certain experiences in how long it normally takes for certain damage to develop, but it can differ a lot. Yeah, that was a bit more about conditions of the structure. Well, we could say we know, and we will never accept anything of a worse condition like this. We know that if everything was as good as we possibly could imagine, then we have the upper limit. We are more convinced that we're probably somewhere in the gray area. And we know it's going to deteriorate, it's going to get worse. We can make some preventive action, give it a new paint, for instance, and it will slow down the deterioration somewhat. If we want to improve things, then we make a repair and we increase the conditions, and then they deteriorate again. And we are still in this gray area because we are not quite sure. And what consequences would be not quite sure have? Well, I can say logically, the ideal repair would be one where you just fix the problem. If there's a problem of, say, water penetrating through the pavement and giving frost damage underneath the pavement, or water and soil penetrating into the concrete underneath the pavement, then the proper repair would be replace the damaged concrete, replace the infected concrete. And well, that would be the logical thing. We would go for a very small budget, but problem is there would be a very large uncertainty because we would not know the extent of the damage, and therefore we would not know the extent of the repair until we actually started the work. Totally difficult to control. So what we normally do is we make a much more conservative repair project. We would, for instance, say, remove all the pavement, remove the top 8 centimeters of all the concrete, good or bad, remove the whole thing, cast 8 new centimeters of concrete and put a new pavement on top of it. This is what we normally do. Because with the low knowledge we have, then that is just about the only thing we can plan for. It's the only thing where we have a chance of controlling the costs. Of course, if it was your own house and you were doing the work yourself, you never behave like this. You would just fix the problems when they needed to be fixed. But that's because you would trust yourself and you would be able to handle it. If we have contractors and contracts where they should do work, then we have to go for the conservative project. Sorry. Okay. Can we improve things? Yeah, of course we can improve things. We can improve things in many places in the infrastructure. Roads, bridges, tunnels, but also power production, sewerage, houses or communication. By learning from some other sectors who have been a bit better, the oil industry and the nuclear power plants, they spend money on maintenance too, but they never have an unscheduled closure of their production. They will plan everything so they can close for, say, 2 or 3 days, and they do all the inspection and repair on that. And that's because they have looked at not so much deterioration as how they can avoid unscheduled breakdowns or delays. by doing that, they identify the real critical points. And they seem to have a much better cost management by doing this proper planning. Yeah, tools for doing this. One, of course, the risk-based inspections, the monitoring, the NDT. NDT stands for non-destructive testing. Well, it can be a little destructive, but it means essentially you can come back and measure on the same thing. If you're taking a concrete core and you're testing its compressive strength, then that is a destructive testing. You cannot test the core again. Then, actually, I would say research and development. This bridge management, well, that's definitely one of the fields where research and development is being used, because there are a lot of money to be saved by, say, the road directorates. Yeah, questions? Okay, I will try to go into a case. I've been talking for almost 40 minutes by now, so we might want a break. Well, I will, don't worry, I'm sure you have looked at the number of arrowheads and said, well, if we spend that much time on the first, then we will be finished about 3 o'clock this afternoon. Don't worry, it will be a bit faster from now on. I'm going to show you some examples from, I would say, a concrete case where we used everything. Highway to farm, crosses the railway around Goltermann station, and there we have 2 old bridges built in the mid-60s, and turned out to be a bad design, exceptionally bad execution, and we don't think there were any supervision. So within 10 years, they realized that they had problems, and they needed some repairs, and they went along with the eastern one first, because, well, we better repair it, and it turned out it took a couple of years to repair it, and notice the cost. It cost 50% of what a new bridge would have cost. Totally crazy. But of course they hadn't expected that cost when they started out, but the more they opened up, the worse it looked. So they decided that the other bridge should definitely never be repaired, except minor repairs. And I would say, that has ever since that we inspected the access, and we have even done full-scale load testing on it. Full-scale load testing is essentially very simple. If the structure had to carry a load, be able to carry a load of so and so many tons, then you place so and so many tons on the bridge, and yeah, well, it didn't collapse. Fine, safety is okay. Of course, we do it a bit more detailed, and we put the load on gradually. But we did that a couple of times. Did some probabilistic analysis of it, and we have inserted monitoring. And I'm very sorry to say you can't see this bridge anymore because they had to give up and replace it. I work for Rumble, and I can say I don't know how many times we inspected that bridge since '75, but we had a contract which meant we had to go out there at least every 3 months to, for instance, remove the concrete that was about to fall down. They hate it when they fall down on the roads. They hate it even more when they fall down on the railway tracks. What we, for instance, would do there would be make an NDT mapping. We take, so we then create a map of, say, this round column. up so we see 360 degrees on the map. And then we can make a mapping of, say, resistance in the concrete cover. Why that? Well, because the more water we have in, the lower the resistance. And we would say, hey, there seems to be an area down here with very low resistance. Yeah, that's not surprising. The concrete looked like this. It's very porous, it's very cracked. We make such mappings, but we, of this, or of corrosion potential, of corrosion rates, but we always combine it with a number of breakups, because this just gives us a map which indicate, well, there will probably be a problem up here. There will probably not be a problem here. Yeah, fine. There's only one safe way of accessing the condition of the reinforcement. That is, remove the concrete and have a look at it. It's the only thing that always works. Of course, we're not going to remove the cover on all the reinforcement bars. That would be stupid. We make a mapping, and then we open up 2 or 3 places. And by doing that, then we can combine what we see with our own eyes. And yes, someone back here, we can map the corrosion potential. That would be down here. There's probably a higher risk of corrosion. We could make a mapping of the corrosion rate, and we would say, here, here, and here, there seems to be a lot of corrosion going on. Ideally, we could use this for a prediction of how fast it's going to develop. We could check the corrosion potential, and we could do it with, say, sensors to see, are there any variation of these over the year? Do we see from one year up to November, and we see some variations of the potentials, but this down here, that would be a high risk of corrosion, this would be medium, this would be low, so the risk of corrosion seems to be fairly constant, even if temperature varies quite a lot. Corrosion rates, that is how fast will the reinforcement actually corrode. Well, with these mappings you can see that, hey, this seems to vary quite a bit. And, well, what we normally say, see, is that, okay, moisture patterns doesn't really change. That means those areas where the most moisture in right now will probably also be the same spots that have most moisture in 2, 3, 5 years' time. Potential, well, the spots with the high risk doesn't really change. Breakups work, corrosion rate seems to vary quite a lot. In that actual column, you could look at the drawings and you could see they have column of about, I think, 1 meter and 10 in diameter. They have put in 25 reinforcement bars of 32 millimeter. Pretty much. But then, when you look closer at it, then you realize that when you cast a foundation, you have some reinforcement bars that stick up, and then you come with your reinforcement cage and lower it on top of that. At this cross section, there were not 25 bars, there were 50 bars of 32 millimeter. I mean, I don't know how. I think we could lose 90% of the reinforcement without any problem. So there were definitely, I mean, it looked awful, but it was not a problem. And that is why we say, okay, check the drawings and the calculation of the actual amount of reinforcement, because you may not need to do anything. It could be one of these spots where there's far too much reinforcement. Oh, sorry, there's never too much reinforcement. There's just far more than we actually need. Okay, the critical span, well, of course it turned out that the critical part of the structure was the superstructure. And the longest span was, of course, over the railway. The most inconvenient spot. If you, for instance, look at this, you will see that part of the concrete has simply fallen off because it's so water saturated that it freezes during the winter. If you took a walk underneath the bridge, it would be totally normal that you could feel the water dripping down on you. The water was running right through the structure. And, well, that was a wonderful structure. Everything wrong. And also the design with these hollow core boxes, and the height inside them were only 60 centimeters. And why is that a problem? Well, if I measure the distance from my kneecap to my backbone, I can say it's about 62 centimeters. This is not a comfortable spot to crawl around. You tend to get stuck. And when you're doing your design of your superstructure, try to imagine how you're going to inspect it. If it's a hollow profile, then you need to get inside it. And the construction workers need to get inside it too. So don't make anything with only 40 or 60 centimeters height in a hollow profile, because it's difficult to get in there. And you're probably going to get in there yourself. Yeah. Well, one of the reasons why they were so interested in this bridge, well, in prolonging the service life of this bridge, well, there were two reasons. One was a new bridge cost about 200 million kroner. If you postpone replacement for, say, 1 year, then we normally say you save 5%. 5% of 200 million, that's 10 million. We can do a lot of inspection for that. The other thing was they knew there were political plans to enlarge the highway. And if they were going to enlarge the highway, then there would be more lanes, and that alone would require a new bridge. So they want to postpone it as far as possible. Because just because the politicians have plans to spend money, then it doesn't mean they're going to do it necessarily. But they postponed it. Okay? That was the case. Your obligations. Well, I would say your obligations. I mean, we have obligations on two levels. One is your obligations in this project. This is beyond what you're required to do in this project, definitely. But if you design a bridge when you're graduating, then please prior inspection, maintenance, and repairs during the design. It's going to affect it. When you design a bridge or anything else, try to identify the critical parts. Critical parts are those where you know you have the highest risk of deterioration. Critical parts are those where you know, for instance, you really know you need all your reinforcement here. You don't want corrosion there. And these critical parts, you must design them so they can actually be inspected. Take a thing like the Link tunnel. Suppose there's penetration of soil did this work? Or you're going to say, it didn't work for these and these reasons. If you see them using something that works, feel free to copy it. If you see something that didn't work for them, try to avoid it. And you're going to be much better engineers. Because, yeah, you're trying to look at how to the future. You're trying to see what you would do in the future. And you do it by learning, also by learning from the past. Yeah. Good. We are now in the last point. That's really the trends. For instance, reinforced concrete bridges, I mean, we have built them in 150 years. They still have deterioration. And some of the things we can do is, we could, for instance, say, why not use stainless steel? When it is a problem that the reinforcement corrodes, then why don't we use stainless steel? It can't corrode. That would be a wonderful idea. We can use so-called cathodic protection. Prepare for it. Cathodic protection is, I said, corrosion is an electrochemical process. Well, then with the cathodic protection, you try to change this electrochemical process so we don't have corrosion. That is really a specialist area. You could try the monitoring, and you could start with a simple approach that can then be upgraded. You can always say, well, I want to be absolutely sure the critical parts are inspectable. Or perhaps say, well, I want the critical parts to be some that I can actually replace. That's no problem yet, but I think they're moving towards it. Okay. Why don't we do all these things in every single project, in every single position? Well, mainly because they are expensive. And that's why we say, well, you build a bridge. You don't have to use stainless steel throughout the bridge. But it would perhaps be a good idea to use it in those spots where we know we normally get the corrosion. I mean, if we have observed it in a couple of thousand or worldwide in 100,000 bridges, then we know, for instance, if we have a road with de-ice and so on, well, then the lower part of the columns will probably have corrosion. The top part of it will not. So we put in stainless steel here, but not there. Same in the superstructure, we know the X-beam and this beam, these places are very sensitive. Well, use stainless steel there. And even sometimes take the bottom here, say, well, no. The column reinforcement, that will still be ordinary steel. Well, the stirrups, well, that could be stainless steel. Obviously, the salt that penetrates into the reinforced concrete from the outside will reach the stirrups first. So make these in stainless steel and these in ordinary steel, and you have probably gained 20 years of service life. We have also tried it on repairs, by the way, and that was really interesting. Stainless steel costs about 10 times as much as ordinary steel in material costs. And ordinary steel is expensive. But then the handling costs are the same, and we had some repair projects where we said, well, okay, it wasn't done right the first time, it's going to be even more difficult the second time. Let's try to use stainless steel. What we found was it only increased the cost of the repair with 1 or 2%, which is nothing. Because you often have 10% variations between the cheapest bit and the second cheapest. So 1 to 2% was nothing. I think it's being used quite commonly by now. protection, well, we can use it to prevent corrosion or we can stop the corrosion. That's simply by interfering with the electrochemical process. And, well, we can have great benefits of that. Again, this is known technology, but it is expensive. And you need to involve some real experts in this. Okay, another case, Øresund link. Well, Øresund link, that's not just the bridge and the tunnel, but we also have some structures here, continuous further. One of the points, which I'm pretty sure you all have seen, is Kastrup Station. Now, what you may not know is the ground, the soil outside the structure, is full of salt. We have also got parking, garages, etc. on the other side of some of these walls. And the walls are, by the way, covered with natural stones, I think it's travertine. This means it's difficult to inspect the walls from this. It's impossible to inspect them from the other side, and the soil is going to come from the other side. We would only observe corrosion here if it was so bad that the travertine blocks fell off the wall. And if it was that bad, then we would close the station immediately, and there would be no more railway traffic from Sweden to Denmark. We don't want to do that. So what do we do? What did we do? Well, we said we will, okay, we will prepare for the other protection. That means just ensuring electrical contact between all the reinforcement bars, and we will insert some sensors. So, and these sensors, in a way, they are exceptionally simple. We have two designs here. These are just simple reinforcement bars, and then we have a reference electrode, so we can measure the potential between the reference electrode and the steel. And, well, we've installed that. We've installed the, I don't know how many places on Kastrup Station. I know there are 200 of them installed in the tunnel. This means we can actually measure the potential and add, I mean, already years ago, that potential was so that we said in normal conditions it would be a severe corrosion. But we could also measure the corrosion rates, and they revealed that there were just about no corrosion going on. So install sensors, and you can actually inspect the otherwise non-inspectable areas. And with these things, I mean, we know the reference sensor has been used for 30 to 40 years. It seems to be doable. The other parts of it, well, that's plain see. We know how doable that is. And with this, we will get a very good warning before there are problems, if there are ever problems. Well, last thing is repairs. Well, we want them to be inspectable because, I said, we are always uncertain about how effective preventive maintenance or repairs are. One of the things we could do is that we could say, well, we could install sensors. We had, for instance, a case with a railway bridge. There were lots of chloride ingress. That was not really the problem. The problem was the chloride had penetrated so far that it had penetrated in behind the anchors for the pre-stressed reinforcement. And we did not wish to remove the concrete behind these anchors, because we would be in serious troubles. What we did was we installed some sacrificial anodes, but we did also make sure to put in a reference sensor. We made sure that we installed enough to actually measure what was happening in here, because the repair ought to work. The sacrificial anode ought to work if the repair didn't work. But there are conditions to at least don't work. And besides that, it's a sacrificial anode. It will work for a number of years, and then it will be gone, and it won't work anymore. So we needed also the sensors, so we could measure if there was a problem. So we could measure how fast it was going to develop. And we could also see that we would be able to upgrade this to work as cathodic protection if we needed to. And we could do all these things without ever breaking up the again. We could do all these things without having any traffic regulations, because we have just installed a few sensors. We have installed the cables out to a small box beside the road where you could always actually sit. Very minor things. I think this cost between 5 and 10,000 per anchor. That was nothing compared to the rest of the cost. And I would say this is, I think, one of the most brilliant things I've seen, because this is like adding 2 or 3 simple things together, and then you have something where you are very certain that at least one of them would work, and you can find out when it stops working, and you can go for another approach with a minimum cost. Yeah? Questions? Now, I'm going to press the last one, which says the end. But Christos will turn up at 10:30. And I think I would like to spend 10 minutes going over a couple of things that influences your design, and which helps you, by the way. So that was the end of the presentation.